we can study the past because the past is interesting, sure. But if we want to study the past to learn more about the future, I think we need to take some steps to make sure that this research really helps. Like, I can look at a certain past because the temperature was the same, but if all these other things were different, so do those steps first to identify the best climates in the past, the best periods that can teach us something about something we don't know yet.
That's the voice of Arthur Oldeman, and I'm Mario Veen, and this is the Interdisciplinary Philosophy Podcast. When thinking about climate change, one of the questions that comes up is how unique is our situation? How unprecedented is it? What can we compare it to? Can we compare it to anything? I was born in the 1980s, and the weather extremes we are seeing now, they're nothing compared to what I have observed, what I have experienced. But how far back do I have to go to find a situation that can serve as an analog, as a comparison to the climate situation that we find ourselves in now? The answer to this question is relevant in many ways. For one, we are in uncharted territory. We don't know what's going to happen now. But if we have a situation in the past that we can compare our present situation to, perhaps we can study that situation and get some clues of what to expect so that we can prepare for it. So the question becomes, how far back do we have to go to find a situation that we compare to our current climate situation? Do we have to go back centuries or millennia, or maybe tens of thousands of years or even millions? Or is there no perfect analog to our present situation? And is it really unprecedented, even unique in the history of the Earth in deep time? This is part of what Arthur Oldeman studied in his PhD research, and we're going to find out the answer to these questions. But let me first properly introduce Arthur. Arthur is a climate change researcher, communicator, consultant, and activist who, after his engineering studies, finished his PhD research on climate variability and atmospheric dynamics in the warm past climates. He writes about everything about climate on his weblog Klimaatveranda.nl, and he puts his climate expertise to use in politics with GroenLinks and activism with Scientist Rebellion. He currently works as a climate adaptation and meteorology consultant at Weather Impact. I hope you enjoy our conversation. Thank you for joining me here, Arthur. Can you describe where we are so that people can place a little bit the background sounds?
So we are in a cafe called Warmoes in Utrecht. I really love this place. It's very artsy. There are paintings on the wall. There's plants everywhere. There's a lot of wood. People are walking around outside, building new things. It's kind of a maker space. It's an interesting place.
And they have good coffee.
They have good coffee.
Yeah.
Important.
Can you tell a little bit about your climate path? I think that's what I called it with Petra Verdonk. We're going to discuss your PhD, climate variability in the warm past. But can you describe how you came to your PhD research?
When I was younger, I always was very interested in environment, in nature. I would go out in the forest with my parents, and my grandpa was a chemist, so I always thought chemistry was interesting. And so when I was looking for a study, I found the study chemical engineering in Eindhoven. So that's the more technology university. And I thought it was very nice because it combines chemistry, physics, mathematics, everything I liked. A few years in the study, I started to learn a bit more about climate change and politics. I realized, I also find that political dimension interesting. And for me, I think a bit of a turning point happened when I was in Australia for an internship, which I really appreciated. My research there was a bit about some chemical reactor. I was designing some chemical reactor that they use in the gas, like with gas and oil, something like that. I was traveling around and I went to see the Great Barrier Reef. I heard stories from my dad about the
When was this?
This was, I think, 2016, 2017, so some time ago. I heard beautiful stories from my dad about the Great Barrier Reef. But when I went there, I was on the boat and the guide was explaining this. Okay, we have to go for an hour into the water. He said before we could go 20 minutes. Beautiful reef. 10 years ago, He said we can't go there. It's white, it's dead, it's hot. The coral is gone. We have to go really far. And we can only do 2-3 trips in the day, and before we could do 10. So he said a lot of our colleagues stopped because they couldn't do it economically anymore. And for me, it was a bit of a moment realizing that, whoa, this kind of warming our planet is affecting people here. I mean, the coral is dying. That's really devastating. At the same time, there are like people in their livelihood dependent on this, and they have to find a different job. Like, it kind of was a moment for me showing the impact of the fact that our planet is warming.
Your oh shit moment.
An oh shit moment. And then I came back in the Netherlands to continue my studies, and I realized all of the lunch talks of my study association and all of the sponsors in this environment at chemical engineering were Shell, Exxon, at Sabic, DSM. A lot of industries that I realized they are part of the problem. And I can choose to be part of the solution. And some of my colleagues think that is at Shell or, at ExxonMobil trying to make this change. But I was not that big on chemical engineering at the moment, so I decided to switch to physics. So I could study physics, and I did a bit of an environmental physics master, which opened up the possibility for me to pursue ultimately a PhD research in climate physics. So this was, for me, a defining moment, then this internship, and then I realized, I have to do something. Actually, this was the same time when Trump was elected the first time. I was there, and we had a good friend in Australia. She was from the US, from California, and she could not believe what had happened. And that kind of, I remember at that moment, I became a member of GroenLinks, so the Green Party in the Netherlands. I was like, I have to make sure that this doesn't happen in the Netherlands. So it was also the start of my a bit more political involvement.
What is your expertise in climate physics?
So I started a PhD in the Institute of Climate Physics. My PhD research was more about climate variability, and this is a broad thing, but let's say variations on year to year, 10 years, 100 years variations. You might have heard of El Nino variations, things like this. And we studied this in climates of the past. So warm episodes, mainly warm episodes, long time ago, millions of years ago. And that was the topic for my PhD research.
How long has El Nino been around? Has that always been there?
Not always, but I think El Nino has been there for at least millions of years. Sometimes it's a bit less active, but it's basically a function of the fact that we have this ocean basin of a certain length. So, like tens of millions years ago, the Atlantic Ocean was a lot wider because of how the continents were arranged, and we had an Atlantic Nino. So, but now we only have it in the Pacific.
And where are we now? We're in August 2025.
Yeah.
Are we still in El Nino?
I think at the moment, don't pin it on me, but I think we're kind of in neutral territory.
Okay.
So I think last year we had kind of a weak La Nina, so it's kind of the opposite. I think we're kind of in neutral territory at the moment.
And does that mean that that's good news for the coming years, if we've looked at all the weather extremes that we've seen?
Usually weather extremes increase with heavy El Niños, sometimes also with heavy La Niñas. Basically, they're deviations from a kind of average climate state, so this neutral state I was saying, and it's kind of going up and down. It actually, what it does, it's kind of a warming of ocean water in the West Pacific, equatorial Pacific Ocean, which seems very specific of an area, but it affects a very large part of the world through what we call teleconnections. So these are connections of the weather around the world, and either through ocean circulation or through atmospheric circulation. So we see these variations in heat during an El Nino it heats a lot, and we can have one year where the surface of the Earth warms a bit more than on average. And actually the past, I think it's 2 years ago when we had 2023, 2024, I think was the warmest year like on record, and we also had El Nino conditions. And this, pretty heavy El Nino actually. And this is one part of the reason why it was so hot. Not the only element, but part of the solution. No.
Yeah, I haven't been studying, let's say, as a layperson, geology for very long, but one of the things that I have difficulty squaring in my mind is that, so on the one hand, I see clearly we're in a climate crisis, but the history of the Earth is so long, it's unimaginable, at least for me, maybe a little bit more for you. Of course, one answer is saying, yes, okay, we're in a climate crisis, but there have been climate crises in the Earth's past before, but humans weren't around, and we just happened to be in a climate crisis, like maybe one of the climate crises before. And it's just that we're around now, and also, by the way, we're also the cause of it. That may also be different. But I have difficulty imagining how unprecedented is this. Because the Earth's history, 4.5 billion years, is there anything sensible you can say about that? How, if you would place our little unique moment at this, or little moment at this moment in the Earth's history, can you say anything about whether is it rare? Is it maybe unique in some aspects? Is it maybe completely unique?
So I can certainly say some things about it. And for me, I always try to, not separate so much, but the kind of the physics side or the indicator side, the things we can measure, temperature, changing temperatures, changing CO2 concentrations, from the impact that it has on human society. I think we are in a climate crisis. Currently, we call it a crisis, maybe an emergency, because of the impact that the physical changes have on humanity. I think that's good to, maybe not separate, but at least to distinguish between those things, because the physics side of it, maybe we have seen some similarities before. Not really. I think that's a good point to start. As far as we can observe, as far as we can say, as far as we can measure back in time, and as far as we can reconstruct the Earth, current climate change is unprecedented, mainly in its rate of change. So how fast we are changing the climate, so how fast we are warming, how fast we are increasing CO2 concentrations, how fast the sea level is rising, how fast the ice sheets are melting. It is really the rate of change that is probably unprecedented, at least on a global scale. Here I already make some details or distinguishments. In terms of temperature alone, let's say we stop warming the planet right now. We are 1.5 degree increase. If we go back in time, we will find a period where it was that hot. So that's not unprecedented. If we look purely at CO2 concentrations, you can go back in time, and we will find a period where that CO2 concentration, the Earth saw it before. So in terms of just those indicators, just those measurements, levels, let's say, just levels, we have seen it before.
You hear people, so we're both very interested in climate disinformation as well, let's put it that way, right?
Yeah.
So one of the things you hear often is, but we're actually in a cooler period, and the Earth has been much, much warmer than it is today. But that's correct, right?
The Earth has definitely been much, much warmer than today, because of a multitude of geological, natural reasons. The fact why it's suddenly a lot warmer now is because of human reasons.
Yeah.
And we didn't have those human reasons before. And we understand pretty well how climate works. We understand pretty well how the Earth works, geology, how interactions between the atmosphere and the Earth cause maybe a heating in the planet in the past. We understand those processes pretty well. And we know it's not causing the warming now.
So if we had a time machine and we could travel to one of these, what's a very warm period in the past?
One of the periods you hear a lot about, because it was really quite hot, is the Eocene, or the Paleocene-Eocene thermal maximum, which was a period around 60, maybe 66 million years ago. And it was, I think, like 10 degrees warmer than the present day.
So if we would have a time machine and we would go there, would we be able to survive there? Would we be able to live there?
Probably not. I think not. No, I mean, apart from, we can go back in time and find a period where we saw these kind of average temperatures, but the whole climate was different. We would not be able to grow crops the way that we do now. We would probably not be able to build houses that are able to withstand this kind of heat. I think that's what humanity just, we can't deal with those conditions.
Sure, but as a single person, maybe you could eat fruits, and I don't even know if they had fruits back then, but
in a very, very kind of theoretical setting, maybe we could survive.
That's one of the things I love about learning more about geology, that you realize, how long have trees been around? How long have flowers been around? How long you start to put these more in perspective, right?
Yeah. Well, so at least this period, humans were not around.
Right.
So we started to be, I think, on the planet, developing around a few million years ago.
Yeah.
Right? So, and still then the climate changed quite a bit until the moment we are now.
Yeah. Okay, so and you're saying, so what's maybe unprecedented, maybe the first time in the Earth's history, is the rate of the speed, let's say, right?
Yes.
At which things are happening, which CO2 levels are increasing, it's warming.
Yeah.
And can you give an idea about how much fast, if before we were on a bicycle, are we now in an electric bicycle, or are we in a race car?
I would say more like a train or something.
A train,
yeah. So we study these periods in the past where a rate of change was also quite high. So certain aberrations, or we have all kinds of names for it, abrupt changes in the past. And one of these was, for example, this onset of this Paleocene-Eocene thermal maximum. But it was quite a long time ago. What was maybe more recent periods of rapid change were the ice ages and some smaller stadials, interstadials. This is more related to the cycle of the sun and the earth and stuff. And we saw pretty rapid changes sometimes also then, but really even the most rapid change, as much as we can reconstruct from the past, currently 10, 100 times faster. At some point we get into an issue that we can't measure on the temporal scale in the past, but that becomes more of a technical issue. Like it becomes impossible basically to know on a 10-year time scale what happened, but in 10 years, 60 million years ago, we don't have that method.
Melanie During, who is a paleontologist, a Dutch paleontologist, she discovered that the dinosaurs went extinct in spring. But it's like spring plus or minus 10,000 years or something like that, right? So if we know it's spring, but the year it could be the whole of human history plus or minus. Yeah. So I find this very interesting. But you study it because you had your oh shit moment. You care about the climate. Obviously, you think this is important for our situation now. Why would you look at such a distant past instead of maybe more recent past?
Yeah, I think that's a very important question. I think that the simple reason. I will explain. So currently we use climate models to make predictions for our future, or we call it projections. We project to the future based on some assumptions of what's going to happen. We understand climate and the weather quite well. However, we are going into climate conditions that we haven't observed in the recent past. So we have a lot of measurements from our climate and the weather in the past 100 years, especially since we have satellites. We have so much data, and we can use this data to validate these climate models and to make them better and to really understand all the processes and then parameterize them in the models. So we know these models are pretty good. in that climate of the recent past. We don't know so well if this climate of the future that we are modeling is very accurate. Because we can't observe the future. And then I'm really mainly talking about these things like, for example, tipping points. Like that might tip, some behavior might change in the future. Maybe the ice sheet melt, maybe the AMOC will collapse. You read about these things. This is hard to validate because it hasn't happened in the recent past. But we have seen a lot of changes in the further past. The more we go back, the more things we may have observed that we might expect in the future. And one of them is warm conditions. The fact that it was warm, the fact that the CO2 concentration was high. This is one of the reasons why we look at the past. And one of the periods I was researching a lot was the Pliocene, and this was a period roughly 3 million years ago. And this was the most recent period that we saw CO2 concentrations comparable to the present day. So in the future, maybe we'll have even higher concentrations. We probably have to go back in time even more. And the advantage, or the nice thing about some of these periods, is that we have reconstructions. We have measurements. And this can be ice cores. They don't go back that far, but what we use, for example, is sediment cores, so kind of little animals in the ocean. They capture information on the temperature, on the salinity, and the CO2 concentration.
How do they capture that information?
For example, in the shells. So these are animals with little shells, and they have like a carbonate shell. And you can see the type of isotopes of carbon, for example, in there, or the ratio of like kind of chemical ratios. And we know that these ratios are dependent on CO2 concentration, for example, in the atmosphere. So we can kind of reconstruct.
Is this biogeochemistry?
This field is biogeochemistry.
Did an episode with Stephen Porter about biogeochemistry, if people want to find out more about how that works.
Yeah, exactly. So we use that field of study, which we also use present day actually to reconstruct or to know some things. But these animals sink, they're on the bottom of the ocean, we drill them out and we can reconstruct the Earth. So we have some kind of information on what the Earth looked like.
Right, so this was about 4 million years ago?
3-4 million years.
What did the Earth look like?
Yeah, so in a geological sense, it was pretty similar. The continents were quite in the same space. Also, the environment was somewhat similar. One of the things that was, for example, different on land was that we didn't have the Sahara Desert, so it was completely green. There were more lakes in Africa also. And some of the ocean gateways were closed. So one of the biggest changes was the Bering Strait, which is currently the strait between Russia and Alaska. It's currently open, and there's a lot of fresh water going through it. And then it was closed.
So Russia and the United States were one country. Putin was right.
It was a land bridge.
Yeah.
So some of these changes were different. Ice sheets were smaller, and this all impacted the climate, apart from the CO2 concentration.
How was the sea level?
The sea level was higher, I think, if I say it correct. Yeah, it was a lot higher because the ice sheets were a lot smaller. So basically, this is the water balance. If it's not on land, it has to be in the ocean. Yeah.
So you look at the Pliocene because there are some conditions that are quite similar to where we are today.
Yeah.
So you can maybe, you can see obviously how that turned out. So you can translate that to maybe our future. Yeah.
That's the concept, right? We try to identify periods in the past that were similar to the present day or similar to the future in some kind of way that we want to learn a bit more about. We identify those periods and we study them to learn more, maybe to test our climate models, to test our understanding of climate change. Yeah.
What was your main method for doing that research?
So my main method was I was using a ensemble of climate models. So let's say something like 20 different climate models that we also use for our present day future projections, basically similar climate models, and they all simulated this Pliocene climate. with the same kind of settings, basically.
That might be new already for people to think about climate models, that you think about, oh, that's how we find out, we can predict which way we're heading.
Yeah.
But you can also do research on climate models on the past.
Yeah, so it is a bit different because you are not modeling the present day, but the past, and the past saw different conditions, and we call those the boundary conditions. And in the way that they are similar is the fact that they are kind of solving the same equations. So the equations we use to describe how the atmosphere moves, how the ocean circulates, and the interaction between the ocean and the atmosphere, how ice interacts with the atmosphere. These equations are the same in the present day and in the past. Yeah. What is different is what we call the boundary conditions. So where are the continents? What was the CO2 concentration? Also, how strong was the sun? All these kind of different conditions is what we put in a climate model, and then we let it run. And then we also have to initialize with certain conditions.
You let it run from what, like 4 million years until 4,200,000 years, or?
Yeah. So to give you an idea, we kind of for this particular project that I was working on, at least, we picked one very specific moment in the Pliocene to tune all of these models on. And this is relevant because you can run a climate model for tens of thousands of years. But what will change also are the parameters like how strong the sun was, how close the Earth was to these obliquity, eccentricity, these kind of cycles change. And we didn't want to deal with that, so we pick a very particular moment in the past that we tune all of these models on, and then we run it for a few thousand years, which in a geological time is not so much. So we can assume that things like CO2 concentration are constant over that time, for example. And then we see what do the models do, and they are often a bit different, and we want to know why they are different. And in some cases they are all showing the same thing, and that gives us a lot of confidence that these things are good. And, yeah.
And what did you find?
Yeah, so what we were studying mainly is the behavior of this El Nino and if it will be different. So one thing that we don't know so much about El Nino is what will happen in the future. So El Nino is changing a bit, and we have a hard time grasping why. Is it going to be more intense? Is it going to be less intense? And we have some kind of geological evidence from this Pliocene that El Nino was reduced in its amplitude. So when it gets hot, this part of the ocean I described before, it doesn't get that hot, right? That's a bit the idea. And that's what the models were also showing me. There was a range of what they simulated, but one of the things that I really saw is that in all of these models, the El Nino variability was reduced or suppressed, actually. And then the question is, why? Is this because the CO2 concentration was higher? And does that mean we can expect it in the future? That was, I think, one of the key questions in my research. And I think I found that probably the answer is no. Which I think is very important to understand. That some conditions were similar in the past to the present day or the future. That's why we are interested in looking at them in the past. But that doesn't mean that it was all exactly the same. So, for example, yeah, it gets a bit technical, but the reason why El Nino was probably suppressed had something to do with the fact that the ocean circulation was different because these gateways were closed, or because the climate was a lot more. How do you say this? Currently, we have a pretty strong gradient between the tropics and the poles in terms of temperature. Yeah. If you warm your planet, this gradient will decrease.
Okay, so the temperature difference with an average day in the north and in the equator will be more similar than it is now.
Exactly. Yeah. So the poles are a lot hotter, and this is something that we might see in the future. Yeah. But one of the reasons this temperature, so we already see it actually in the present day in the Netherlands, for example, it's heating a lot more. In the Siberia, is heating a lot more than at the equator. So this gradient
Too bad
slowly.
All the ice is there.
Yeah, exactly. Well, but this is it's nice that you say it because in the past, especially in the Pliocene, we were coming from warmer conditions. Yeah. Let's say, hundreds of thousands of years before that period, which meant that the ice sheets were a lot smaller, and because of these gateways that were closed, there was no sea ice, and this was actually one of the main reasons that it was even more warmer in the poles, because this white ice sheet and this white sea ice reflects a lot of sunlight, but then it was a lot darker basically, and it absorbed a lot more heat, and that's why it was even warmer, and that's why this gradient was decreased, and this is not a condition that we will see in the near future. So I thought that was interesting to find. Like, we really had to dive into these models. How are they working, and how are the conditions different? And we know this because we can tweak these models. It's kind of a nice tool because, I want to simulate the past, but what I can also tell this model basically is, okay, simulate the Pliocene climate, but with a different CO2 concentration, or maybe with this gateway open or closed. We can do these kind of sensitivity tests, and then we're not simulating a real climate anymore, but that is to kind of figure out how sensitive is the climate to these changes in conditions. And we use that information to know that it is, A and not B, the reason for this El Nino being different finally, yeah.
And when you do this, it's like kind of almost playing God, right?
In a way.
Does it feel, the physics expression, shut up and calculate? So you're just calculating and not thinking about, this is an actual period that happened, and are you just really busy with the technical aspects, or do you have some kind of connection or feeling about, this was 4 million years ago? And
yeah, actually, for me, I found that really hard in my PhD research. So for all these years that I was studying this, I found it very hard to imagine what this climate is like. It's so hard to imagine what a climate of
do you think
millions
it's
of years
important
ago.
to do so? Or is it just a nice extra?
I'm not sure how important it is, but at the same time, when we are studying, or if we are studying the past to inform our future, and I made some of these comparisons, like, okay, I saw in the Pliocene certain conditions were similar to, a climate scenario in the future under certain SSP scenario. You find these similarities, then I think it becomes important to be able to understand what did this world look like. Because then it becomes a bit more real. Then it becomes, we can expect these conditions. We cannot expect this whole past climate to get back, but certain elements of it, yes. And I think that makes it valuable to try and imagine, which is basically impossible, but to try and reconstruct as much as you can. Okay, what was this like? Could we live there? Probably not really. Humans were not around.
But maybe, we could live there in the sense that we could breathe the air, right? And there would be vegetation.
Yeah, exactly.
What kind of animals would eat us?
I think there was some of the things like crocodiles, for example, were around already
They've
for a while.
They've been around for a while, yeah.
Yeah. So, and there were some mammals also, big mammals.
Yeah.
So could we have lived there? Yeah. Could we have lived there with the world as we know it now? No. Yeah, but that's also the future. And I think a lot of people don't realize that. If we keep emitting and if we keep warming the planet, we are going to futures where we cannot continue living like we do in the present day. Which is a very uncomfortable message, but we don't need to look at the past for that. That's something I always try to communicate. It's very interesting. We can learn so many things from the past. That's why we look at it. But we don't need the past to tell us that we're on a bad path.
Can you speak a little bit more about that? How you see what's going on in the world now?
In terms of
the climate, obviously we're also interested in the political dimension, but what can we expect? And what can we do about it? Just like very, like your elevator pitch about this.
Okay, we have another hour now. So I think we already see climate extremes temperatures that we don't like, drought conditions, crop failures, wildfires. We already see many things happening and more in the news. That's now. It will only get worse. Except if we stop emitting now, but that's not going to happen. I think we should always keep some kind of hope and strive towards keeping our planet as livable as possible, but we also look at the geopolitical situation, and it's probably not going to happen tomorrow, right? If you look at current policies, so what you can basically make a bit of an estimation, like if we look at the current policies and promises that politicians have made, or really concrete actions, we can expect a warming of around 2.7, maybe 3 degrees at the end of this century. It can be less if we do more. It can even be higher if we do more to prevent it because of feedbacks in the climate system. That's a whole other topic. But 3 degrees of warming compared to pre-industrial conditions, so let's say 2 degrees more to present day, would be really devastating. Like, I think people don't realize, because we talk about these temperatures, but we don't live in an average temperature. We live in seasons, we live in a daily weather, and this is what will be disrupted. The weather will be completely disrupted, which will impact ecosystems that we depend on, which will impact crops that we try to grow. I think a lot of people fail to realize how dependent we are on this stable climate. Humanity, the way that we grow crops and stuff, we have developed this over the past thousands of years when it was a very stable climate conditions. Only then could we as humanity really boom. And now we are changing that so fast. It's not just we insulate our houses a bit more. It's not the only thing. It's really affecting so many things. And once it happens, we can't just turn back. That's something that really scares me. And I think a lot of people either don't realize or they don't want to think about it, that this is something that is happening. It's easier to put your head in the sand and focus on short-term economic profits, which is what I think what a lot of politicians are doing. It's a lot easier. And then once we get to those conditions, once we really see how devastating it is for everyone in the world, we can't just turn back. And that scares me.
So the moment people experience it, then it's too late to still do something about it. In a sense, it's already the case, right? I mean,
to a certain extent, it's already the case. Yeah. Certainly. We are already seeing people that are, let's say, dying in excess because of us warming the planet. Because of heat, because of crop failures, because of floodings that we can attribute to climate change.
I had a similar realization when I was reading your thesis. I felt like, of course, we're concerned with the future, right? That's because that's where our children live and our older selves. But then I realized, of course, you can use the same models that we use for the future. We can examine the present and maybe learn more about it. Yeah. And I had a similar realization with reading Frederike Otto's book Climate Injustice. I'm going to do an episode about climate attribution as well.
Oh, wow, yeah.
Where she starts out her book with, I think, she's going to talk about how much worse, the degree to which climate has affects what we are seeing now, right? Recently in June in the heat wave, I think World Weather Attribution Service said, 2/3 of the people who died in 12 European cities can be attributed to climate change. Yeah. But she starts out actually the book about speaking about the 1930s. And even it makes perfect sense. But of course, the more we learn about this tool that we didn't need before, in this case weather attribution, but in your case climate models, we can also look at how what was it, the droughts, the dustbin in the United States, and these kind of things. Even these events were made worse by, or more extreme by, climate change, which was already happening there. Which means that people have died in those conditions that would not have died without climate change.
Yeah.
That's what I find very fascinating about your research as well, is that because these models are simulations. But you're not, you're simulating, but you're also just very aware of, but the coral reefs are no longer where they used to be.
Yeah. I think for some of my, I found this a very hard pill to swallow, to be honest. Doing this research every day, looking at papers, articles, whatever, about how bad it is. Every day, and in a very scientific way, described in papers. I think most people probably don't read scientific papers on, how bad climate change is. But this language is not very appealing or very engaging, very dry descriptors of, X many people might die, these kind of things. I found it very hard sometimes to read that every day, and I see my colleagues, my ex-colleagues at least from where I worked, used to deal with this in different ways. People would sometimes present a new research on the amount of tropical cyclones that would increase, and we would all laugh about some kind of mathematical or statistical funny thing or something, and we would all be laughing there. And sometimes I would walk out of these meetings and be like, this is crazy. But you become numb to it to a certain extent, and it's very scary. I think it's very scary that you become numb if you work on it so much. I think a lot of my colleagues, I try to speak out. I try to do climate communication because I realize more people need to know this. I think if you are in a bubble where everyone works on climate change, it's not a surprise anymore, and it becomes numbing, right? And I saw a lot of my colleagues were like, I don't feel like I want to speak out so much because, what's the point? Or I'm not the expert on this particular topic, or which is fair. Everyone should make their own choices regarding that. But I also found it a bit, hard. We have so much knowledge, and a lot of people don't care to share it so much.
So it does sound like, to some degree, at least you don't numb yourself to it.
I don't. I found it, it did numb me, I think, a bit, but it also made me anxious and scared sometimes at night.
Yeah. And what do you do with those kind of feelings of maybe frustration, maybe anger or fear or something like that?
Yeah. I mean, it's many different things. I think sometimes it's anger, the fact that we let this happen with all the knowledge that we have. It really angers me sometimes, which is also very frustrating because you don't always have a place to put that. But for me, I engage on social media with people, I write articles and blogs, I'm active at the political party, I join demonstrations, I organize, I mobilize, I try to do as much as I can that doesn't overwhelm me, let's say, to try and make a bit of a difference. And these things also help me to process these emotions.
Mm-hmm.
Yeah. It's heavy, but I can't. I think the thing is, I realized at some point. I mean, I had a burnout in my PhD, and I think one of the reasons was this. I also just did too much work and too much other things, but I was just very overwhelmed with everything. And a realization I had then was, I can't change the world on my own, even though you want to. You sometimes just would like to be able to make a difference or make a change and be the one person that presses the button and, okay, it's done. But you can't. And that's sometimes very annoying. And you see other people that do have the power to make a change make the wrong decisions. And that's very frustrating. But I can't change the world alone, right? I can do my part and I can try as much as I can. But if that means I'm burnt out, if that means that I'm depressed, then it's no use anymore. And I mean, I can say this now that I went through a period like that. But it did make me realize, like, okay, the impact I have is small on my own, but together we can have a big impact.
Yeah, well, one of the things that helps me is at least to so of course we have knowledge, right? But one of the things which I think you also do in your PhD is kind of coming up with useful concepts or distinctions to think about our situation, how to relate, in your case, how to relate the past to the future and the present, right? It's a very strange roundabout because the future is very close.
Yeah.
In the past, we need to take urgent action, and the past you're looking at is millions of years ago. So, I mean, doing research on climate and time, I find that very interesting. One of the things that I thought, okay, I kind of know this, but I think these are very useful distinctions just to think about climate change in terms of maybe just take a step back, because I want to speak about the distinction between forcings, processes, and response.
Yes. Okay. Yeah.
So why you need them in the first place? Because you started out by discussing how unprecedented is it, and in a way it's unprecedented, but there are certain analogs. So well, first of all, what is an analog? It is not sometimes I read analogy. I'm a little bit dyslexic, but then no, it's analog. What is an analog in your field?
Yeah, so we study these paleoclimate analogs or climate analogs. Of course, analogy is a broad concept, but in the field of climate, what we consider an analog is two periods, for example, that were similar. So maybe the present and a geological period, or the future and the past period. And if they are similar in a certain way, if they are similar in maybe CO2 levels, for example, they could be considered an analog.
Yeah. So you can say what happened there might also happen here. That's the way that's analogous, right?
Yeah. So it's based on this concept of what you can call predictive analogy or analogical reasoning or logical inference. I think it's all a bit the same. The fact that the fact that you find two periods and they are similar in one thing, and that probably means that they are similar in more things. So if I don't know something in the future, but I know that the past period was similar in this one thing, then maybe I can predict what happens in the future based on what happened in the past.
Right, and then we need to take one more step to something we discussed a few times also in the podcast, uniformitarianism.
Oh, yeah.
Right, a very important concept in geoscience. Maybe you can speak about just very short what it is, but also, is it still valid? Is it still a valid way of thinking?
Yeah, I think uniformitarianism, as much as I know about it, is a bit of a concept in geology that everything we know about climate and the Earth will be valid now and in the past and in the future. So let's say the laws of physics are invariant. They're not changing with time. I think that's a bit the idea of uniformitarianism. So anything we know about the present day, that's actually where it started. There were geology researchers studying the past and trying to reconstruct the past based on these very few kind of measurements or proxies that you have of the past. And they used this idea like, okay, we know a lot of the present day of the Earth because we can measure everything, and everything that is valid now must be valid in the past. And so they use that
because
concept.
we cannot, just to state something very obvious, we cannot just take a literal time machine and go millions of years back.
Yeah, we can't measure all of that.
So we are always studying something in the present, like a rock or some chemical reaction or something.
Yeah, exactly.
And by studying something in the present, we can say, but if it happens, the way CO2 reacts with, I don't know, something else.
Mm-hmm.
That will also have been the case there.
Yeah.
The way mountains form, earthquakes happen.
Exactly. Yeah.
So, and I don't remember exactly what you said about it, but I think there's also, you nuanced that a little bit, right? Is that still the case? Because we talked about, but what if we are in an unprecedented situation in a sense?
Yeah, I mean, this uniformitarianism is a concept. It's a bit of a theoretical framework. That doesn't mean it always holds up. I think the laws of physics might be the same. How the tectonics works will be the same, right? But there are differences in the different periods in the past. There are differences in the future, and a lot of these differences are, kind of also a balance of factors. And I think when this uniformitarianism can go wrong is the fact that maybe we know our present day climate really well, and we know all the elements maybe that go into an ice sheet melt, for example. We know the things that are important, the ingredients that are important, but it could very well be that there is kind of one piece of the puzzle that we just don't really see now because of how the climate currently works, that might become relevant in the future. And then we miss this piece of the puzzle. And you see this, for example, in things like these tipping points that are currently, very slow processes that we are just in the middle of, and it becomes very hard for us to make any kind of useful predictions because we've never experienced this tipping before. And so it becomes very hard for us to make any useful predictions because we might go into some kind of climate state. Maybe the Gulf Stream, the AMOC will collapse, and it might go into a new kind of state or situation that we have not lived in.
And then if you're if you say a fundamentalist uniformitarianist, then you would say, no, we cannot speak about tipping points because show me the tipping point now. I don't see one. So,
Yeah, I mean, I think it depends a bit on the scales that you're looking at. Like on a larger scale, the physics and stuff might be the same, but in a more practical, smaller scale, systems can be different. Processes can change. And we can learn things from the past. Actually, that's what we try to flip with this concept of uniformitarianism. What we, at least in my research, were saying, whatever happened in the past will be valid in the future.
Okay, so now we're taking a little bit of a roundabout, but now we're getting... So you state several times that, citing also a lot of other research, that no perfect analog exists in the Earth's deep past. And then you could say, but then the whole endeavor is useless. So that's where I found this distinction useful between the forcings process and response. I remember. Can you speak a little bit about that? How you can use that for partial analogs?
Yes, of course. So in this whole concept of analogical reasoning, you might not require that the whole Earth is the same. It will be kind of an impossible endeavor to do. But you might be very interested in one particular thing that might be the same. And then the question is, what is that thing? And we identified doing this research on analogy that there's different things that you can consider if you want to look at analogy, like what has to be analogous, what has to be the same. And the most useful, or not most useful, but most often thing is in terms of levels or in terms of response. So the level of CO2 concentration or the level of temperature that we can measure, is that level the same in the present day and in the past? And then you're not considering this rate of change or the processes or whatever. You really look at this level and you can find similarities. And then we try to distinguish a bit a response versus forcing and process to make this analogical framework a bit more useful or practical when we are comparing the past with the future. So a response can be, or let me start with the forcing. What we consider forcing in climate science is things that determine the actual climate, things that determine the actual weather, maybe. So, for example, the sun. We cannot control the sun. It's kind of an external element to climate. The power of the sun, or the radiative forcing, that's also what we call it, that's kind of coming in, it's forcing our climate system. And ultimately, we will have a certain temperature response. So that is what we experience. That is what is a result of this forcing, is the temperature at the surface of the Earth.
And why don't you just call that cause and effect?
We could have. I think it's more of a terminology thing. And I try
but
to...
that's how I can think about it. That's the cause of why the climate is the way it is, or changing the way it is.
Yeah.
And the result of could be volcano eruptions or anything.
Yeah, so I mean, it's a terminology thing, but it might be useful to distinguish. And then also, what you mentioned is this process, so the process through which this happened. So in terms of if we have the radiative forcing, so the sun, the whole process that we can consider that leads to this temperature effect, cause, response, is the radiative balance in the atmosphere. So the sun comes in and Earth loses some heat, and this is in the balance, and the ultimate outcome of that, the ultimate response is the temperature we measure. And there are just different ways of looking, making a separation to what you... Like, we can be very interested in finding a period which has similar CO2 concentration, because CO2 can be considered forcing the level of CO2. We can also be interested in looking at temperatures. But then we might be interested, if the temperature was similar in the past, was this because the forcing was different, and how was it different? So, and that's kind of new
really
to
like
my...
puzzle pieces, like you look for maybe the forcing here and the response there, and there's another period.
Yeah, and at some point it becomes very complicated, I must admit, because it's a very big puzzle to piece together. But what we try to, and it's a bit of a new element in I think in my thesis, because before my thesis, basically a lot of people, when they look at climate analogy, when they're making these comparisons, let's say, between the future and the past, is they really look at temperature, for example. Also because it's something you can measure in the past or reconstruct. And then if you find a climate that has a similar temperature, you say this is an analog. But if you don't look at why this temperature was the same, was it because this forcing, which forcing, was it because these gateways are different, what I was talking about, ice sheets, or was it really CO2 concentration? If you don't consider that, it might still not teach you so much. And this is one of these parts of this analogical reasoning. I'm not sure who it was, but someone distinguished a bit this kind of potential for generalization, I think it was called. If you don't consider other things that might be relevant, you might not be able to use this analogy. Maybe I can give a bit of a practical example. Actually, I was thinking about this morning. How can I explain that concept? Let's say you look at a car and you see it drive. There's two things. You see how the car looks, that it's a car, and you see that it can drive. And then you look at another car, but you don't see it drive. But from your experience, you could infer that it will be able to drive. That's kind of the analogy. It might not, because of a variety of reasons. One thing could be that the car is upside down. It's lying on its roof. Maybe the wheels can spin, but it won't go. It won't move. And this is this concept of potential for generalization, I think. So you could look at one thing and see it's similar and try to infer something from the past onto the future. But if other conditions were different, and they are also important, then we might not be able to use this analogy. And that's a bit what I try to communicate with my thesis and with this research. Like, it's not so simple.
Well, one thing that makes me more optimistic is that there's still so much to discover, right? Because this is pretty basic, I think, right? I mean, not basic in the, but more fundamental. Like, how can we use the deep past to learn useful things that we can use for the future? And apparently there's still a lot to discover.
And I think, yes, for sure, there is so much to learn still, and there's so much data. There are so many periods in the past that we can focus on. There's so many things we can study. And I think one of the things that I tried a bit with this analogy research in my thesis is to make the focus a bit better. So if we can study the past because the past is interesting, sure. But if we want to study the past to learn more about the future, I think we need to take some steps to make sure that this research really helps. Like, I can look at a certain past because the temperature was the same, but if all these other things were different, so do those steps first to identify the best climates in the past, the best periods that can teach us something about something we don't know yet. So, for example, some of my colleagues were doing research on, or some other climate researchers are doing research on AMOC tipping. So this tipping of the AMOC, of the Gulf Stream, which happened somewhat recently, like a few thousand years ago, during ice ages, and then we could consider this some kind of analogy because there was AMOC tipping. It went on and it went off. It went and a few times. It was in a bit different kind of climate state, different background climate. So maybe it was not the potential to generalize. Maybe is not there completely, but this process is interesting. The process of AMOC tipping will be something that we can learn something about. And I think you can identify these periods. This happened. We can figure out why, and then it will teach us something about the future. Yeah, so it's really to try and inform these things better. We can learn so much, but yeah, we need something now to make better projections and stuff.
Yeah. You finished your PhD last year, I think.
Yeah.
What are you focusing on now?
Yeah, so currently I'm working at a small company, and we do climate consultancy in a very broad sense. You were talking earlier about impacts on humans and this kind of crisis element, and how certain extreme weather conditions can lead to disaster. Also, there's research from Freddy Otto is a bit about that. I try to make a bit this link between extreme weather and how this leads to a risk and how this leads to a disaster. So my work currently is a bit more about trying to inform governments, but also, for example, farmers in South Sudan, in Ghana, like what you can do to adapt to climate change, and how can you make sure that this hazard, this flood or this drought that will be coming, how can you make sure that this doesn't lead to a negative experience? And well, there's a whole variety of things that you can do, and sometimes you can't do so much because it's very intense, but it's a bit more in the field of climate resilience, climate adaptation that I'm working on now. So it's a bit more applied, but and a bit in the field of development, I guess, but it's still using that kind of climate and meteorology knowledge that I got from the PhD.
Thank you so much for this conversation.
Thank you.